what we have done last time. So we did consider a quantum thermalization process, but it was a little bit fast and mostly in Mathematica. So I thought I should summarize it a little bit. So what we did was we had a region that we call top, and we had a region that we call bottom, that we can think as a reservoir. So we start with some bosons in the reservoir, and then at some point we open a small door that allows the bosons to start going and spreading and thermalizing the rest of the room. So it's the analog of putting the gas in a corner, holding it there, and then releasing it in and letting it thermalize. So what was the model then? These were bosons, and they were called hardcore bosons. That apparently it's something that not everyone was familiar with. So let me emphasize what this is. This is nothing fancy. So what are they? These are the states that are generated, that they are spanned by a creation operator that creates a boson at any site n1 up to nk. So this would be a state with k bosons. And they act on the empty lattice to create states at position n1 up to nk, for example. And what's special, what's hardcore? Hardcore means that if you create it twice, you get 0. So it's not possible to put two bosons at the same position. And they commute, so that's why they are called bosons. Now, of course, this is the same. If you don't like this, you could just say that if I measure position, how many electrons there are at site I, let's suppose I add to the Hamiltonian something which suppresses enormously putting excitations, putting more than one excitation at the same position. So I would just put some huge term times I would count how many excitations there are. So this would be just saying they are bosons, so they can be on top of each other, but they repel so much that in practice they never are. So when I consider now 5 bosons, what happens? So they need to be somewhere. So the energy will be 5 times U, because they need to be somewhere. But if they were to be on top of each other, sorry. No, this just says that bosons don't like to exist. This is just a chemical potential. I would have to put something different, sorry. Put something like that would really suppress them being at the same position, like the position square. So now if they are 1 per site, it just costs 5U because they are 5 at the 5 positions. But if 2 are at the same position, that costs immediately 2 square, which is 4. So it costs much more energy for them to be at the same position. And then they will never be. They will just be moving around without occupying the same site. Okay? And then, of course, the Hilbert space now would be much bigger, but the states where they are occupying the same position would be projected out. Okay, so then, what was the Hamiltonian then? There is a hopping term, meaning that boson can be annihilated at site I and created at the neighboring site J. And there is a term that counts bosons at site I and J that are neighbors, and that penalizes a little bit the energy, which means there is some repulsion between neighboring bosons. And that was the Hamiltonian. Then what was the game? Our wave function can be decomposed into eigenenergies with any coefficient Cn and then the usual time evolution in quantum mechanics. And what we impose is that at t equals 0, we start in the ground state of the reservoir, which is psi 0. Now, what is the ground state? Let's emphasize something important here. So the Hamiltonian on the bottom, what is this Hamiltonian? It's the Hamiltonian where I sum only over the lengths of the bottom, so I didn't open the door yet. It's equal to energy times the wave function. Again, that's what it means to be in the ground state. Now, if I act with a full Hamiltonian on this state, it is not the energy times this state, because there start to be new terms where the boson was here, right? The boson was here, and it moved inside. There was a door, and the terms where the boson is right by the door, now they can hop into the big region. And if I act twice with Hamiltonian, now 2 bosons could move inside. Right? Actually, is this true? Could 2 bosons move inside if I act twice with Hamiltonian? So let's see what happens. One could go inside, right, if I act once. And then I act twice. And now what happens? First, that boson needs to go away because they are hardcore. So if I want another one to go inside, I first need to act twice with Hamiltonian, such that the boson goes in and then moves inside. And then I act 3 times, and now the 3rd time a boson can go in. So if I imagine acting with Hamiltonian several times to generate time evolution, they slowly start moving inside. But just acting twice, it's not enough to bring 2 bosons in. I act 3 times, and I get 3 bosons in. But immediately when I act with an Hamiltonian, they start coming in. One gets in. And because one gets in, this Hamiltonian is not, this state is not an eigenstate of this Hamiltonian, which is good. That's what we wanted. Note, however, that when we compute the expectation value of the Hamiltonian on the initial state, that is equal to E0. Because now that I project on the initial state is orthogonal to this state because it has no bosons there. So this is actually still true. And this is the energy at any time this expectation value is conserved. Right? So this is just conserved in quantum mechanics. If I put here h of t, if I have to replace this by psi of t, this is obviously the same, right? Because the evolution commutes with h. Is generated by h. Okay? Yes?
Sorry, I don't think I understand what h bottom is. Like, can you write it down or?
Yeah. So this is a summation over all links of my lattice, right? And h bottom is the summation over only the links in the bottom. So this link here is in the full Hamiltonian, but is not in the Hamiltonian for the bottom. They are exactly the same. They are just bosons moving around, except that in one the door is open, the other the door is closed. So there is a hopping term between those 2 guys or not. Okay? More questions? And then what were we seeing? We were seeing that if I compute some expectation value of some observable, some O, so we compute this expectation value in time of some observable. So what is this? So by definition, it's equal to a summation over n O n times absolute value of Cn squared plus sum over m not equal to n O m Cn Cm So by definition, if you have any wave function, this would be the expectation value of the observable. And what were we seeing? We were saying that this was given, if I were plotting, that it starts far from equilibrium because I release the bosons, and then it oscillates around some value. Now, what was that value? That value was very close to some expectation value of the operator O in the microcanonical at fixed E equal to E0. That is, I could imagine that instead of doing a time evolution of one state, I could imagine my energy is E0, right? My energy is E0, and I sum over all states of energy E0. So what is this quantity here in microcanonical? This quantity is the summation of N, O, N over summation over n, which is just counting the states. And this summation is over states whose energies, En, are roughly E0 plus some small term, E0 minus some small term. And the idea is that this window should not be too small, because if it's too small, there is no energy which is equal to E0. But it should not be too big, otherwise it's everything and it doesn't make any sense. So it needs to be smallish, but not too small, this delta. Right? So this is what you do in a microcanonical ensemble. Then you get that line over there, and that's what it approaches. Right? And that's indeed what we would expect. Now, on the other hand, okay, so what does it mean? So the hypothesis is the following. What seems to be happening, or at least one way of explaining this, is that these quantities here, that normally you could think that should depend very non-trivially on the details of the state, they seem to be just equal to O in the microcanonical ensemble as a function of the energy that is involved there. So if this were to happen, that these guys were approximately equal to these guys, and if these guys were small, if 1 and 2 are, so 1 plus 2 are what people call the eigenstate thermalization hypothesis, which is the idea that even one state alone knows about the microcanonical ensemble and they know about thermalization. Okay. And that's what we expect. That it should not be so important to sum over states or to just evolve a gas from a pure state in a room. Of course, we do observe the thermalization in the usual way. Okay. Now, what would be the line if I were to compute this in the canonical ensemble? Well, forget about thermalization. What we said in the beginning of the lectures was that computing it in microcanonical and in canonical should give the same thing, at least when the lattices are big. Here the lattice is not huge. It was 21 sites. And therefore, the canonical prediction would be some line close to this one, but not exactly the same. So this would be the canonical prediction for this operator O computed in canonical. Remember, what does it mean to compute something in canonical? It means that you don't fix the energy. You fix a beta, a temperature beta. And how do you fix this temperature beta? You fix it such that at that temperature, the average energy is E0. Right? So that's what it would mean to do it in the canonical. So we compute this observable in the canonical ensemble at a given beta such that the energy expectation at that beta is equal to E0. And we know that these two guys would be equal at large systems, but the system is not super large, so this here would be related to square root of the number of degrees of freedom, which in this case like 21. So it's not that small, so it's a little bit bigger. This is if I consider some observable which is extensive, and I'm normalizing by the number of degrees of freedom. Right? Like energy per site or something. Yes?
Could you repeat why you would expect these two conditions, the wave code 1 and 2, to be true?
So 1 and 2, if 1 and 2 would be true, they would imply that it would thermalize in this way, because fluctuations would become suppressed, these oscillations in time, and because if by itself each of these states already works, then I can remove them out of the sum. The sum of c squared is just 1, and it would work. So 1 and 2 would imply this figure, but this figure doesn't imply 1 and 2. There could be other hypotheses. other ways that this could work. So this is like the simplest condition that would imply this figure.
Okay, so
Now going from this figure, this is reality, right? Real life is like this. We start with a state, we evolve it, it looks thermal. So this is definitely true. The question is, does this imply this? And no one knows. No one could prove. And that's why it's called an hypothesis. Eigenstate thermalization hypothesis. Right? Not theorem.
It's a large time phenomenon, right? Can you mention something?
It's a large time phenomenon, but what's nice about ETH is that it's not about complicated time evolution. It's just a statement about expectation value of observables in the eigenstates of the Hamiltonian. So it started as a complicated time evolution thing, but now it's just a statement. Quantum Hamiltonians have this property, that expectation value of observables are smooth functions of energy, and off-diagonal elements at the same energy are small. At different energies are small.
Are those off-diagonal elements time-dependent at some point? Because
No, this is just numbers, right?
then shouldn't that imply that I should see the convergence very close to the initial times?
Very what?
Like if you have at short times and
Yes.
you have only off-diagonal elements to be small, shouldn't I expect that convergence to happen very fast rather than long times? Because you only have an oscillating time factor there, right? That exponential. But if you're only assuming that the off-diagonal terms are small at any time, then I shouldn't expect this to work only at large times, right?
Okay, so Andres is pointing out where do we see that there is some time where it starts working and before that time it was not really working. That's related to what does it mean by small and so on. If they're super, super small, it would be right away. The point is that phases help you because they decohere, and even if this is smallish but not so small, because you are adding random phases arbitrarily, it helps cancel this term. So they don't need to be, when I say small, I didn't quantify it, okay? And random phases would help a little bit, so it doesn't need to be super small. Okay. But anyway, I just want to say this because if you read a little bit the papers that I sent in the wiki, I find them quite beautiful, and people are often confused about, especially about conceptual issues, about the importance of being in an ensemble versus being in a pure state, and I do think that it's very important for people to have in mind that pure states already thermalize, and that if someone tells you that I'm considering the following experiment where the state is, the room is in a canonical ensemble, but if the room was in a pure state, the conclusion would be totally different. You should be suspicious, because we see that thermal and being in a pure state, it's almost indistinguishable. And that's what people often do when they discuss paradoxes in black hole physics. They make a huge fuss about being in pure states versus canonical. So it looks like it's very suspicious. Okay, very good. So now I wrote it in the back blackboard because we are now switching gears. So we will not need to see this anymore. But just to say that, just to emphasize again that this is where we see this thing is quite nice, and this is what we would call thermalization. The fact that once you know that it thermalizes to some ensemble, the fact that these curves are similar is just equivalence of ensembles. Which is also interesting, but it's a different business, right? It's a different story. One thing is to check equivalence of ensembles, another thing is to check thermalization. So today in the tutorial, you are asked to take the code that we run and to just add this line with a canonical prediction to see that it also converges to the canonical prediction. Okay? So that's what you will do in the afternoon. Okay. So we'll switch gears a little bit, and for the next few lectures, we will be studying one statistical mechanical model, which is the XY model. Okay? So So we already encountered the XY model in the lectures, but I did not give it a name so far. And the XY model will occupy us for the next at least 3 lectures. Okay. So this model is a model where the Hamiltonian is minus j sum over I and j neighbors as I dot sj, where these guys are unit vectors with 2 components. Okay. So at each side I have a vector which has 2 components, and the 2 neighboring sides I have some 2 vectors, and there is an angle here compared to this vector here. And so, sorry, let me write like this. So I could imagine. So this angle between the 2, if this is I and this is j, this angle here would be theta I minus theta j, this big angle that I drew there. And my Hamiltonian is just minus j sum of cosine of theta I minus theta j, that where thetas are the angles at each of these spins. Okay. Now, why am I saying that we already discussed this model? Because this model is in the same universality class of this Mexican hat if I'm really in the situation where we had our table, and remember that there was x at position n component 1, x position n component 2. This would be the case for n equals to 2 and negative mass. And then there was this Mexican hat potential. And what did we know? We know that the vectors, they want to have some size and then rotate freely with that fixed size, right? So it costs energy to change size. So we could very well say that this is a vector of fixed size if I want to study the low energy physics of this model. So saying that it's a unit vector, which means that it has fixed size, you could say that it's very much related to this when I suppress this fluctuation. So at low energy, this would be the same. Okay? Right? So at low energy, they are just where the fact that it's unity or a fixed length is the same, it is just renormalization of this coupling J. Okay? So this model, yes?
Could you repeat why it has to be at low energy?
Because if it's at very high energy, these fluctuations that were suppressed, they would be excited. So like saying I am in the ground state configurations were configurations where I'm in the valley of this Mexican hat. This is the minima of the potential. And then physics are things that move in the valley, but they don't start going up or down. That costs lots of energy. Okay, so remember that these excitations here were gapped and these ones were gapless. So it costs lots of energy to excite these longitudinal modes. They had a mass. Whereas these transverse modes, they had no mass.
I'm not sure I understand why it's in the same universality class.
So you remember, for example, when... so I didn't prove it. So it's, because these things you can never prove. I mean, you can just compute in both models and see that they are in the same universality class or argue that they should be, which I'm trying just to argue, I'm not proving. So, but you remember that, for example, for our table, when I said that I had 2 possibilities, the table was slightly up or slightly down, right? And then I said, well, if it's slightly up or slightly down, it looks like just an Ising model, where at each side I just say, is sigma plus 1 or sigma minus 1? And then I said, both are in the same universality class. I also did not prove it, right? I just said that if I have a model where some regions are plus 1, some regions are minus 1, that looks like from long distances it should describe the same physics where I also have small fluctuations around that. So similarly here. Here, it's not true that the vector has a fixed length. It has a fixed length and can oscillate a little bit. Right? But I'm saying that, okay, from far away, what matters is not these small fluctuations, because they cost energy, but rather the rotation here. And if that is true, then I would say they are in the same universality class. So it's by the same argument of the in class when I said plus minus 1. Is it clear?
I think so.
Okay, good. But you can say that this is a starting point. I mean, this could be our starting point. We don't need to relate it to our table model, but if we relate it to the table model, that's how we would relate it to the table model. We would say that there is some rotational symmetry. Okay? Now,
Is this in a two-dimensional lattice?
okay, so far I didn't specify it, but let's consider this model in a two-dimensional lattice. Then it would be exactly like our table. Now, one of the beautiful things of this model, if you remember, there was something cool when we started exploring these universality ideas, which was that the same model could describe sometimes various things, right? Like we had this magnetic model where it's plus 1 minus 1, or we had a table which could be slightly up or slightly down, or we had a fluid of particles where the sides could be empty or full, and all those were simply related to each other and they were describing the same physics at long distances. Here as well, we will see that this model is related at large distances to beautiful physics that we wouldn't have guessed. For example, this model is in the same universality class, as we will see tomorrow, as a Coulomb gas of charged particles. So if you have a gas, you put the gas of charged particles in a plane, and this Coulomb gas of charged particles is in the same universality class as this spin system, right? Who would have guessed from looking at this? You just have some spins at each side, and now I'm telling you it's in the same universality class as a gas of Coulomb charged particles. So this model has, yeah.
Is there a table then in the same universality class as the Coulomb gas?
Yes. The table with the 2 degrees of freedom, yeah, it would be. Yeah, this is definitely true. Not the table we studied. The table we studied just had up or down. It didn't have n equals 2 rotation. Not the table we were studying. Okay. Now, let's see. So our goal is to study this model for a while, and the plan for today is to study this model at high temperature, at low temperature, combining both observations to make a guess for the general physics, for the physics of this model, and then tomorrow we'll start quantitatively verifying these guesses. Now, before, let me just make a comment that J positive or J negative is the same, basically. Right? And this is true, at least it's the same in a cubic lattice. That's a nice idea that you should have in mind, that sometimes you could think that it's very different physics, J positive or J negative, because in one case it looks like the spins want to align, and in the other case it looks like they want to anti-align. So it looks totally different, right? But it's actually the same, because this lattice is bipartite. So if I have my lattice, I can separate it into a sublattice A that just couples to sublattice B. So these guys here, if I call this guy site A, they just talk to site B and they don't talk between A and A. Right? So if I say that spin at sublattice A, if I redefine it as minus S prime as subsite A, what it will do, if I just redefine, if at the sublattice A, where I see a spin, I call it minus S prime, this is just equivalent to flipping J to minus J. Because J only appears coupling A with B. Right? So there is no difference in the physics of plus J and minus J. Right? In other words, if you think they want to be plus, minus, plus, minus, plus, minus, just call the spins at site minus, just call them minus S prime, and now they are all plus. So there is no difference in the physics of this. And that's because it's bipartite, because there is a sublattice A that couples with sublattice B, and there are no interactions between A and A. Okay? Okay, so here it is crucial that this is bipartite. Okay? So this is not particular to this model only. Any model of this type, if the spins were not continuous but discrete or something, it will be the same thing. So J bigger than 0 or smaller than 0, it's basically the same. So that's good and that's bad, because the bad thing is therefore that different books will choose different signs. And since I use different books to prepare the lectures, you can imagine that sometimes I might have some wrong signs if we don't do the computation carefully. So let's try to be careful. Okay. Any question here? Okay. So what do we want to compute? We want to compute the partition function, say, which would be what? It would be the integral over, at each position of my lattice, I integrate theta at that position from 0 to 2 pi. Right? So that's what I do for each side. And then I get exponential of minus beta times energy, so of beta j summation over neighbors I and j cosine of theta I minus theta j. So that's basically the object. This is really the object we would like to study. Now, this model cannot be solved exactly, and it has a huge amount of physics despite its very simple appearance. And today we start exploring it in the limit where beta is so high temperature, so beta small. So let's try to do it. Okay? So if beta, I'm considering this statistical model, and if beta is very small, so let's normalize each d theta by 2 pi, right? Because the integral is from 0 to 2 pi. Then my z is approximately 1. I just put beta equals 0, and the exponential becomes 1, and I'm integrating 1. D theta over 2 pi gives 1.
Sorry, could you repeat that?
Just beta equal to 0 becomes 1. And then it's d theta over 2 pi. For each theta gives 1, 1, 1, 1, 1, 1, 1. So this is just equal to 1. So we could ask, what corrects this as I expand in theta? So let's postpone this. Let's postpone these corrections a bit. And let's ask, what would be, in this limit, the expectation value of the spin at some position j dotted with the spin at some faraway position j plus n. So what is this? This is the expectation value of cosine of theta j minus theta j plus n. Do you agree? Which is actually equal to the expectation value of e to the I theta j minus I theta j plus n, because the cosine is two exponentials, but we have theta to minus theta symmetry. So both exponentials give the same, so I can keep only the first one and multiply by 2. And now we see that if I plug this quantity, right, I would insert it here, right? I would insert it here and integrate over theta. But what? So if I replace just beta by 0 in the exponent, what would the integral over theta j give? You see, I just plug one. I compute this average, which means I plug this exponential here, and I want to do the integral over theta. I put beta to 0, so I kill the exponential. And now I have integral over this theta. What's the average of e to the I theta? 0, right? So the integral will just give me 0, right? So this is going to be small. And how do I not get 0, right? So now we have to note that, how do I not get 0? So e to the I n theta. So if I integrate over theta, this is non-zero only if n is 0. Right? Therefore, when I put these two terms, you see what happens. What happens is that I need to expand this beta out and bring down some exponentials that cancel this e to the I theta j with e to the minus I theta j. So let's draw the lattice and see how this would work. So suppose I have some lattice here. And I start here at some position j. And this would be some position here, j plus n. So here I have only e to the I theta at position j. Now what I could do is from this link here, let me color it in orange. And what would this link be? This link, if I expand in beta, it's 1 plus beta j cosine of theta j minus theta k, where k is this side here, plus dot 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 order beta squared. And that's equal to 1 plus beta j over 2 e. Now I'm going to write the negative exponential first. E to the minus I theta j plus I theta k plus e to the I theta j minus I theta k. Now you see that what's happening is that this exponential now could multiply by this exponential here and cancel the theta j dependence, right? And now the integral over theta j would give 1 rather than 0, right? But then we have a problem that theta k is here. Right, so yeah.
Sorry, what is this quantity you're computing?
This.
But with on that link, that's why you're computing across that orange link?
Okay, let me be a bit slower. So expect this quantity here. No, thanks for asking. This is very good. If you have questions, otherwise it could be too tricky. So this is the expectation value of e to the I theta j minus I theta j plus other position, which is equal to what? To the integral over the product d theta at position n over 2 pi to the number of integrations, so L squared. And then I plug this quantity here, e to the I theta j, e to the minus I theta j plus n, and then e to the minus beta h, which is that exponential over there, divided by partition function. Right? So this is what we want to compute. Now, the integral over theta j wants to give 0. Because the integral. So what I need to do is from the exponential, bring down one term here from the Hamiltonian, from that link, that would give e to the minus I theta j. Because then e to the I theta j times e to the minus I theta j, now the integral over theta j no longer gives 0. But then the integral over the neighbor, over this theta k, would give 0. So what I would have to do is bring down another link, say this link here. And this link here now would be 1 plus beta j over 2, and the relevant term is e to the minus I theta k plus I theta L, where L is this term here. Do you agree? So all in all, I see that for this guy not to be 0, I need one link to be neighbor. Then for the next guy not to be 0, I need again to expand down a link. And how will it finish? It will finish when I connect the 2 points by a path. So it could be, say, this path. Right? So this would be a path connecting j and j plus n. So from that path, if from each link I expand to leading order in beta, I'm trying to do the first term that is not 0, so I expand to leading order, I see that indeed I get a non-zero contribution from that path. Right? So what are we getting? We are getting that this is equal to the following, to the sum over paths that connect j and j plus n. For each path, I bring down this factor of beta j over 2. So I get beta j over 2 to the length of the path. Right? And then what do we get? We get times 1, where this one is integral d theta j, d theta k, d theta l, etc., all divided by 2 pi of e to the I theta j. I start with theta j, but then I do minus theta j plus I theta l, so these two guys cancel, and the integral gives 1. and then e to the minus I theta L plus I theta k, so that these two guys cancel, and therefore the integral gives -1, dot, 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 all the way to e to the minus I theta, let's call it R plus I theta j plus n, e to the minus I theta j plus n, where R would be the next to the last site. Right? And so this would give me just 1. Right? So that's what we would get to leading order. And therefore, what paths are the ones that are going to dominate when beta is very small? Well, it's the smallest one, the ones that have the minimal length. Right? So this will give me equal to beta j over 2 to the power of the minimal length between the 2 points between j and j plus n times the number of paths with that length. And that would be the estimate for the correlation function between spin at position j dotted with spin at position j plus n. Okay, this would be an important result. But what's important about this result, it's not really the details of the formula, but to see that it's exponentially suppressed at large distances. Right? It's e to the minus the length times some number when the distance is large. So that's what we get at large distance, exponential suppression of the correlation between spins at 2 positions at high temperature.
Sorry, did you just set the z that's on the denominator to 1?
Z in the denominator, yes, it was 1, right? 1 plus small corrections. More questions?
I'm so sorry. Could you just repeat the argument where we get the summation over paths? How do we? What do you mean by taking down an exponential?
Okay. So we are expanding at beta small. So when we expand at beta small, it means we Taylor expand quantities in beta, right? So all these integrals are compact. They are between 0 and 2 pi. There's nothing fancy. I just go to the exponential and I write e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus dot, dot, dot. And I just expand it down, right? That's what it means to expand. Now, when I expand down, so to compute a partition function to leading order, I don't need to expand. I just set beta equal to 0 and I get 1. So the terms that I'm expanding down are subleading in beta very small. Because beta equal to 0 already gives me 1. Is it clear? Or no? Yeah. Now, when I compute the correlation function, however, I do need to expand down, because if I don't, if I just do the integral of this quantity, I get 0. The average, this average is 0. So how is this average non-zero? Well, whenever I bring down one interaction from the Hamiltonian, each term in my Hamiltonian here, whenever I expand it, I get 1 plus beta j times cosine. I just brought it down from the exponential. I just expanded the exponential. And this contains 2 terms. One that is irrelevant. So this term is irrelevant for what we are doing. Why? because you see that if you multiply it, you only made the problem worse. Instead of e to the I theta, you get e to the 2I theta j. So if you integrate over theta, it's still 0. Now this one, on the other hand, you have e to the minus I theta j plus I theta k. So multiplying by e to the I theta j, now it no longer gives 0 when integrating over this first position, but it gives 0 over the second position. So I need to expand down another link. For example, this one, but it could be this one. It could be any link that connects to this point. But I expanded this one. So now this integral is giving 0. So I expand out this link. But now this is giving 0. So I expand and I go on until it closes at the other end. Now, I could have chosen a very long path going here, 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 here. But that path will have more powers of beta brought down. So that would contribute way less. But that's what I wrote here. I wrote that we sum over all possible paths, but each path gives beta j, which is small. Remember, right? This is small, 0.11, to the power of the length of the path. So paths that are very long are super suppressed. The ones that matter are the ones that have the minimal length between j and n.
So this, when you write that this is exponentially suppressed at large distances.
Yes.
If you are in the, that's for beta really small, right?
That's right. That's what we are doing. Beta small.
Okay. Yeah. So it won't be valid for.
No, it will not. And that's crucial because what we are doing is we are saying what happens at beta small. Then we'll ask what happens at beta large. And we'll compare both and see, well, then something in between should happen. That's what we are doing now, is trying to understand the physics by exploring some limiting cases. First, beta very small. Next, we'll do beta large. And then we'll try to see what's the difference between the two and how do I get some hints about what's going on. Any question here?
Actually, one question.
Good.
Is this expression, the second to last line where you write it as a sum over the paths, etc.
Yes.
Is that one exact?
Good. So, not really. It's the leading contribution. And because it's the leading, it doesn't even make sense to keep the paths that are not the minimal ones, right?
Okay.
So the minimal one. But to understand your question, we could ask z is not 1, right? 1 was an approximation. So what would z be? So let's think a little bit more. Let's try to make it exact. So this was an approximation. But let's suppose we wanted to compute z in the high temperature expansion. Okay? So z is defined as integral product d theta n over 2 pi. And then let me write actually something that maybe it helps. That Hamiltonian I can write as a product over links. And then each link is just e to the beta j cosine of theta I minus theta j. Right? This is the same as the original Hamiltonian. So it's a product over all links. And what we did when computing a correlation function between 2 points is said, for most links, I replace this exponential by 1. But for the links that connect point j and j plus n, I cannot. And I have to expand them out to leading order. Right? That's what we were doing. Now, this guy here is, as we said, 1 plus beta j over 2 times e to the I theta j minus theta I minus theta j plus e to the minus I theta I plus theta j. Right? So if I take the 1, I get 1 for the partition function. That's the leading order term. Plus dot dot dot. But suppose I take the term with beta. So suppose I expand my Hamiltonian and I say I want to expand my term and consider the contribution from this link. Where by this line here, I mean this expression here. I expanded and I got this term in beta. That's a correction. Now, you see that now if I integrate over theta I and theta j, I get 0. Integral over theta I gives 0. Integral over theta j also gives 0. So if I just replace one of the links by this expansion, I get 0 right away. Which means that I have the same problem as before. These two ends are open, and therefore the integral is 0. So what I could do for this guy is say I also expand the neighboring link. And now this guy is no longer 0. But I have the same problem. I just delayed the problem. It's this endpoint and this endpoint that are problematic now. So how could I get a non-zero contribution? Make a closed loop, right? So for example, this. Right? So what would this closed loop contribute? This closed loop would give me beta j over 2 to the power of the length of the loop right? And then you see that for this loop I could pick this first exponential, which would be like keeping one orientation of the loop. If I pick this exponential, then the other ones, it's obvious which one I need to pick. But I could pick this exponential, which is like picking the opposite orientation. So that will be a factor of 2. And this would be the orientation of the loop, which means which exponential do I start with? And then once I pick that one, everything is fixed. Right? So then this z would be approximately equal to 1 plus summation over all possible loops beta j over 2 to the length of the loop times 2. And this I would say it's a summation over a loop. But actually, I could have plus 2 loops, for example. Plus dot dot dot. And so we would conclude that here in the high temperature, we interpret this as a gas of loops. Now, you could complain about something. You could say, what about the dot, dot, dot in this expression here? This is as if we are just taking the leading term. So what about this dot, dot, dot? So, and that's true, indeed, they are there. And therefore, this picture is a little bit more complicated. So this is only morally roughly correct. But in any case, if I want the leading term in beta, it is true that the leading term in beta is just 1 plus a smallest possible loop of 4 units. That's the smallest loop I could make, plus other terms that are suppressed. And in any case, we are never going to use this. For us, for our approximation, it's just 1, because we only care about the leading approximation. But this is a general feature of these high temperature expansions. In the high temperature expansions, you often get this gas of loops. So maybe I'll just say I'll just make a comment on how we could make this treatment of gas of loops more rigorous in this XY model. So what's annoying here is when I expand cosine to some big power, I have to to decompose it into positive frequencies and negative frequencies if I want to write this gas of loops. So one thing that we could do is the following, is use the following expression, e to the beta j cosine theta, it's equal. You can check this because I don't remember by heart, but it's something like this. Okay. So this is just an exact expression where I'm just Fourier transforming this object. So this is just an identity, that this Boltzmann weight is just equal to this expression. Okay? Where, if you want to check, let me tell you that at beta going to 0, this in of beta goes like beta to the n, where these ins are Bessel functions. It's just an identity. Exponential is a generating function of Bessel functions. So these are just modified Bessel functions. So it's I in mathematics. Bessel I. Okay, these are some known functions. So let's check. So to leading order, so this, if it's true that in is just beta, to leading order, this is just 1 from this guy, 1, and then, because I want the leading order, I just take the term with n equal to 1 here, and I get plus beta, okay, there is beta j, of course, beta j, plus beta j times e to the I n theta plus, sorry, e to the I theta plus e to the minus I theta. And this is just from the term n equal plus minus 1. And that's the leading order term, which is what we used, plus dot, dot, dot. What is nice about this way of writing is that in this way of writing, you see that downstairs I just have exponentials, right? So now the integral over theta is trivial to do. The integral over theta is done using just that formula. It is 0 if n is 0, otherwise it's 1. Right? So you see that now, because of this, when you expand it down, it's like at each link, you have some strength n. So it's like your loop. It's not only connecting two guys, but it's connecting with a loop, a string of type n. It could be of type 1, that's what we did for leading order, of type 2, of type 3, of type 4. And if you put a link of type 4, for this not to be 0, it means that here you need to put 4, here you need to put 4, and here you need to put 4. So you have to sum not only over loops, but over loops of different thickness. And that would be this n. And in fact, more rigorously speaking, what happens is if you have n times theta, at some point this n times theta could break into n minus 1 here and 1 here. These two exponentials would still add up to 0 in total. So you have a gas of loops that have some thickness and that can open up and spread, and it's a more complicated gas. But from this expression, you could now go to a rigorous representation in terms of loops. Okay? All this is just to give you an idea of how it works. So from this expression, we could easily go to some loop gas. Now it would be easy to just integrate over the thetas and to write this partition function as a sum of gas where the weights would be given by this product of these functions that we could call Tn's. Okay? And that would be a generalization of everything we said so far. Yes?
The correlation function depends on the length, on the minimal length, wouldn't, like it depends on the details of the lattice. Right?
It does. At high temperature, it does depend on the details of the lattice, yeah.
So wouldn't it be reasonable to sum over like the all possible lattices or something like that?
No, that no. We start with a material, it's just one lattice, right?
Okay, so
We have a crystal, it's one lattice. We don't sum over crystals. We fix it. But you are absolutely right that it does depend on the details of the lattice. I'm going to comment on that soon. But for now, I just want to say that to write a rigorous loop gas expansion for the XY model, it's possible. Then you can write that the full partition function is literally a sum over loops. Okay? And the full two-point function is the sum over paths, where not only I have paths, but I can have paths in the presence of loops. And there could be loops around, because I can have the path, and I could also bring down a loop, and the loop could be there as spectator. Okay? And the paths could then touch the loops and interact with the loops, and it would be a loop gas. But to leading order, I just replace partition function by 1, paths by minimal paths, and that's it. Okay? But the punchline of this, if you want, is that I could reformulate everything in terms, there is a representation where the full partition function is equal to a loop gas. Okay, I think, given that this is a nice point, maybe I'll make a small parenthesis. And comment on, so let's open a small parenthesis before continuing our analysis and discuss the two-dimensional Ising model, where what's the difference now? My z would be, instead of integrating over thetas, I sum over sigmas that are plus or minus 1. And then I have product over all neighbors, I and j, e to the beta j sigma I sigma j. Right? So that's exactly the analog of that first line in the middle blackboard. Right? And I sum over all such configurations. Now this expression here, you see, it can take value when sigmas are both the same. This expression is e to the beta j if sigma I sigma j is equal to plus 1. Or it's e to the minus beta j if sigma I times sigma j is equal to minus 1. Right? So it only takes two possible values. So I can write it, this expression, I can write it as a plus b sigma I sigma j, because it only takes two possible values. And I can fix them right away, because when they are the same, it must be that. So a plus b is equal to e to the beta j. And when they are different, it must give this. So a minus b is equal to e to the minus beta j. Right? So from this, I get that a is cosh and b is sinh of this quantity here. Do you agree? And now you see that, right? So I can write this as a times 1 plus b over a. I will actually do the computation, which is tangent of beta j times sigma I sigma j. So let's call this quantity here alpha. So what is my partition function then? My partition function is equal to a to the power of the number of links times the summation over all sigmas that can be plus or minus 1, and then product over I and j, 1 plus alpha sigma I sigma j. And alpha would be small in the high temperature limit as before, in the high T, which corresponds to beta going to 0. So beta small, tangent is small, alpha is small. And this is exact. Here there's no approximation, right? But you see that this formula here, now it has the property that this partition function is therefore a to the number of links, of course, times 1 plus dot dot dot. Like our partition function was 1 plus dot dot dot, because I just replaced beta by 1. Right? But now what is this dot dot dot? Dot 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 comes from taking the terms with powers of alpha in the links. But it's exactly the same argument as what we had there. That if I take this link, I must be careful because sum over sigma I of sigma I sigma j is equal to 0 because I sum over plus minus 1. So if when I expand down I pick 1 power of alpha, I get 0 for the same reason. It is just that sum of sigma I plus or minus 1, right? This is equal to 0, right? It's sigma j minus sigma j. Right? So the only way I don't get 0 is again if I don't take 1 alpha, but if I take a loop of alphas. Right? So the only way I would get non-zero is if I say that I get this dot dot dot, where this dot 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 is equal to the sum over loops, alpha to the length of the loop, and that's it, right? In this case, it's actually just that. Because when I have a loop, what do I have? I have sigma I, sigma j, then sigma j, sigma k, etc. And each of them just gives me trivially 1. And so, sorry, actually, not completely, so let me be more careful. So it gives alpha to the length of the loop. And then the loop, I multiply out the sigmas, right? I, j, j, k, k, l, l, until I close. So I get 1 because sigma j square is 1, sigma I square is 1, all sigma squares are equal to 1. But I still sum over what values they take. So I get times 2 to the length of the loop, because the summation gives me 2 to the length, so it's 2 alpha to the power of the length of the loop. Okay? So this 2 is like the internal sum over the loop. Okay? And in this summation over loops, we have 1 loop, we have 2 loops, etc. And here this would be an exact result. If I keep the sum over all the loops, there's nothing, no approximation here. And you see that this expression here, this decomposition here is rather trivial. It's what replaces that complicated one with Bessel functions. So the fact that the model is non-compact, instead of having just 2 nice terms, because there were only 2 possibilities, now there are infinitely many, so if I do want a loop gas, it becomes more complicated. So this loop gas would be the generalization of this, with the detail that this very simple decomposition became a very complicated one because we have infinitely many Fourier modes. Okay? Okay, but this is just a parenthesis that the 2D Ising model is can be written as a loop gas. Whereas our XY model, let's call it some generalized loop gas. It's a loop gas which has more degrees of freedom. But both have this property that to leading order, also in Ising, if I have two open indices, sigma I and sigma, I would also sum over the paths that connect these two guys, and the leading order one would be the ones with the minimal length between the two, exactly like above. So that the analysis will be very similar. That's why it's useful to know it, these high temperature tricks. Now, as your colleague is pointing out, this does depend on the details of the lattice. So let's do two examples. Let's do one example, points could be here and here, versus another example where the points could be here and here. So if the points are here and here, there is only one path which has minimal length, which is this path here. Right? This is the path with minimal length. So in this case, I would get beta j over 2 to the power of the length, which would be some horizontal length between the two. Whereas here, there are many distances that are the same. This is what is called, these distances on the lattice. You see, this distance here, this path, has the same length as this one. Right? These paths, they have the same length. So these paths have the same, it's also called taxi length or Manhattan length, because you see that it's the length that if you were a taxi and if these were buildings, that would take to go to this, from this building to this building here. It doesn't matter if you go straight and then turn, or if you do a diagonal. If these are streets, it's the same total length. Right? And that's the length that would appear. So in this case, what would we get in this case? In this case, we would get beta j over 2. So let's say that this distance is L and this distance is L as well. Now we would get this to the power 2L. Right? This is the total distance of either of these paths. But how many paths are there going from here to here? Can you tell me? So how many are there? So it's how many ways are there to go from this building to this building. And what you would say is you have to go 5 blocks or 4 blocks in 5 blocks in this direction and 5 blocks in this direction. That's how you describe to someone, right? Go 5 blocks that way, 5 blocks that way. Doesn't matter how you choose. If you go first 5 blocks, then 5 blocks, or if you do first 5 blocks like this, then 5 blocks. So out of the 10 steps that you have to do, choose. So out of the 2L, choose L to go straight and L to turn left. Right? So you can go straight, 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 and then left, 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 or straight, left, straight, left. So you have to make 10, you have to give 2L steps, and you choose which ones to go straight and which ones to go vertical. Yes?
Why couldn't you have a path that went left and then turned back on itself?
A path that went left.
And then went right again. So you
Right, back again?
left, up, right, like a long path.
Okay, so that is a longer path, because then it would come with a higher power of beta.
Okay, yeah.
Yeah.
How does it work if we have like periodic boundary conditions?
Well, if you have periodic boundary conditions, if this period is much bigger, nothing happens. But if it's faster to go through the other side, we would go through the other side. So we would just find what paths are minimal in the periodic lattice. Okay? And therefore, this goes as e to the minus length divided by some correlation length. And this one goes as e to the minus L divided by some other correlation length. So by the way, this at large L, this is just something like 4 to the L at large L. And then, sorry, let me not, yeah, okay. Let me write not, okay. Let me write distance. Where this distance, in this case, for example, is square root of 2 times L, because they are in the diagonal. And here, this L is the distance between the 2 points. So what we conclude is that in both cases, we see well that it's exponentially suppressed, but it's indeed not isotropic. It depends on the details of the lattice, okay? Because of this taxi driver distance versus usual distance. Okay, so it doesn't decay exponentially in all directions.
Sorry, what's the distance you're normalizing then?
Sorry?
What's the psi?
It's defined by this expression. So for example, here, right, this is just e to the minus L times logarithm of 2 over beta j, right? So it's exponentially suppressed in L, and this is what we would call 1 over this horizontal scattering length, for example, in this case, to indicate that at which length does it start to be really exponentially small. Okay. So this would be some horizontal scattering length, and this would be some diagonal one. And more generally, it would depend on the angle of where you are, and you could easily compute, but it would, in any case, always be exponentially suppressed with the distance, which is just the length of the path between the 2 points. Okay. So that's what we see. We see exponential suppressed at large temperatures. Okay. I have 5 minutes, right? Yeah? Okay. So now let's see what do we expect at low temperatures. So at low temperatures, we would say that we are close, so low temperatures means large beta, and therefore our partition function, I would guess, should be well approximated So what would we expect? When beta is very large, these guys, they want to be aligned. They want to be pointing in the same direction. And we would expect that when we are close to the ground state, there will be small fluctuations of these guys around the equilibrium position. So we would expect this to be approximately equal to beta j sum over ij 1 minus theta I minus theta j square over 2 plus dot dot dot, because we would expect small fluctuations. So this one is just normalization of my partition function, and therefore we would conclude that this partition function is just proportional to the integral over theta e to the minus beta j over 2 sum over I and j theta I minus theta neighboring square. That's what we would expect. But we have to be a little bit careful here, of course, because here, what this looks like it's describing, this looks like describing a massless particle in 2 dimensions, right? Remember that there is no quadratic term. There is no here theta j square with some m omega squared over 2. No term here. And this was what we were getting, therefore, in our previous examples when we had this mass effective square equal to 0. So we should be a little bit careful here, because what would it mean to say that the theta's are very close to each other? It would be saying that the spins are all pointing roughly in the same direction. But we said this was not possible, that we did not have spontaneously symmetry breaking, that the spins will not start pointing all in the same direction. If I start doing that, fluctuations are much bigger than my starting point, so they immediately say that the assumption was wrong. Okay? But here we have some hope of being able to control these fluctuations, because theta start becoming very big, but thetas are periodic, right? So let's go on with the approximation, knowing that when the fluctuations are very large, we don't trust the approximation anymore. So let's see what this, let's continue with what this low temperature then would tell us. This is written here. This was not the lowest. They are all written. Okay. Okay. Anyway, so the point that here we are getting a Gaussian model. Okay. This is what is called the spin wave model. The spin wave, because we are thinking that the spins are very close to each other and they only move slowly like a spin wave. See, like some spins that are roughly pointing in the same direction, moving slowly. Yes?
I'm a little confused about what you said at the beginning of lecture, where we're allowed to switch the sign of j, because it seems like this is different if you switch the sign of j.
Yeah, good point. So you first fix the sign of j. So with a given sign of j, the thetas will want to be either parallel, or theta j will want to be pi plus the other theta. So flipping the sign of j is shifting theta by pi. But in that case, you would not expand around the value of the argument equals 0, but you would expand around the other critical point of the cosine, and therefore the pi would cancel, because in the expansion you would have theta minus pi. So j positive or negative would mean expanding around maximum or minimum of cosine, and you would have an extra pi from the other point that would cancel the pi in the other case. But we are choosing a sign that thetas want to be parallel, and therefore the natural expansion is both thetas around the same value. Okay? So the other two choices are thetas want to be the same, or one theta wants to be pi plus the other one.
Okay,
so let's choose the ones where they want to be the same.
it's not that you get the same thing, it's just that it's equivalent.
Exactly. It's equivalent, yes. In other way, in one case you have spins that move slowly. In the other case you have one spin, the neighboring one is pointing in the opposite direction but similar, and the other one pointing in the opposite. So you would have to do a transformation, spin to minus spin, but they are equivalent. Okay, very good. So this model is Gaussian. So I want to finish this computation now, which is, let's compute in this approximation the same average we computed before, spin j plus n. Okay, so exactly as before, I do exactly the same approximation. All that is true. So this is equal to the expectation value of e to the I theta j minus I theta j plus n. And I'm computing this average in a Gaussian model. Right? So this average we know how to compute, right? This is just average of an exponential in a Gaussian model. So maybe you don't recognize it right away, so let me just remind you. So we are just going to compute that integral, and then we will be done for today. let me remind you that the expectation value that we have there is nothing but the expectation value of j dot x in a Gaussian matrix model. That is where I integrate x1 up to xn, and I have some quadratic term, and then a source times j. Right? So this was what we computed before. What was this? This was e to the 1/2 j a minus 1 j. Right? So that's exactly what we have. Just don't be fooled by the fact that here, this is, in this expression, this is just the expectation of e to the j dot theta, where j k is delta k j minus delta k j plus n with some i's. Right? Then this becomes, that expression becomes that expression. Right? Is it clear? And therefore, this average here, that average there, which was the correlation of spin j and spin j plus n, is exponential of 1/2 the first current that says that delta k is at position j minus delta. So there is an I minus delta k is at position j plus n. Then the inverse of my matrix, but the inverse of my matrix was nothing but the propagator between sides propagator j plus n minus j, which is just n. Remember, the propagator was the inverse of the matrix of this quadratic form, times the current again. Sorry. If I want to write it in this form, I want to write this as jk I minus 1 kl jl. So I should write the propagator between sides L and K, and then my current I delta Lj minus I delta Aj plus n. So you see that this term sets K to be J, and this term L to be also J, then the propagator will be at 0. This term times this term also set L and K to be the same. It's also propagator at 0. And the cross terms would give propagator at separation n. So in total, I with I gives minus 1. This would be exponential of propagator at separation n minus propagator at separation 0. And this is equal, and we already saw it once, but we are going to see it again in the next lecture more carefully. See next lecture as well. But you remember that this g at large distance was logarithmic, right? This propagator in the 2 dimensions was logarithmic. So we would get exponential of logarithm. The coefficient is the inverse of what appears there. So there is beta j over 2. So what would appear here would be 1 over beta j. There would be some overall number from inverting this propagator. And then logarithm, there will be a minus sign, and then logarithm of the distance at large distance. And therefore, it would be 1 over the distance to the power some number over beta j. And what this is now not exponential, but now we have a power law decay with a continuous exponent. An exponent that changes as I change the temperature. So that's very interesting because it's not a single power law, but it's a family of power laws that depends on the temperature that would have there. And this is what we would say, it's a line of critical theories. That would depend continuously on what beta we are. So let's erase this corner and summarize what we saw today. So what we saw is that as I change the temperature, when I am at high temperature, I have exponential decay. That is, it's typical, it looks like a gap phase where things decay exponentially. But when I am at low temperature, it looks like I have a family of massless, that is, critical theories with power law decay. And therefore, the idea would be that here there should be some transition. And the hint is that what is happening is that we have this low temperature approximation. What was wrong? What could be wrong with it? What could we be missing in this approximation? Is the fact that theta is periodic. We didn't take this into account. So why would we not just have power law always? Why wasn't this just something good that would just be corrected? And the idea is that here we are missing, as we increase the temperature, we are missing some important configurations where the periodicity of theta is strongly explored. And these are what are called vortices. Vortices are configurations that locally the spins are changing smoothly, but are introducing some topological excitations in the system where the spin would change a lot. And these guys, we totally ignore them in our low temperature analysis. And the intuition is that as you increase the temperature, at some point these vortices start appearing. It starts to be favorable to create these vortices. And these vortices will screen your correlation functions and will make a transition between a power law decay where things were decaying long length, and now because of these vortices in the middle of the two spins, they screen your two spins and they give an exponential decay. And that's how we would go from high T, how we would transition as I increase the temperature from a power law decay to now an exponentially suppressed. Okay? So the idea, the guess, our guess right now is that as T increases, perhaps what happens is we have some proliferation of vortices driving a phase transition. And this is what we are going to explore in the next lectures. And this transition is called the Kosterlitz-Toulouse transition. And that was the subject of the Nobel Prize 2 years ago. So it was given exactly for understanding this transition between these two regimes. Okay? Let me just finish by saying one thing. The last thing I want to say, which is what would happen in higher dimensions. In higher dimensions, what would happen at what would happen? The critical thing is the following. At very high temperature, the same business. You just expand, but now you have to sum over paths in 3 dimensions, for example. Fine. You just sum over paths, but now they are in 3 dimensions between 2 points, right? In your cubic lattice. Still exponential suppressed. Okay, that's the usual high temperature physics. It's always exponential suppression. But what about low temperature? Low temperature, very different. This computation is exactly the same. So up to here, nothing would change in higher dimensions. So this expression here, this would be the same in d bigger than 2. But the key difference is that, however, the propagator, g goes to infinity in d equals to 2, or to minus infinity with the correct sign, and therefore, in d equals to 2, s went to 0. And what is ss? What is the correlation of spin at 2 very different positions? Well, at 2 very distinct positions, this is just expectation value of s times expectation value of s. They are very, very decoupled. So what are we seeing? We are seeing that in 2 dimensions, you cannot have an expectation value of the spin. And that's what we knew before. That was Mermin-Wagner. That was saying that you cannot have long-range order. You cannot have this expectation value, right? So these expectation values are 0. The difference is that in higher dimensions, in d bigger than 2, this propagator goes to 0 instead. The propagator decays with 1 over r to some power. And therefore, this goes to 0. This g of 0 stays here. And therefore, this s now would go to a constant. And that's order in higher dimensions. And that would be the fact that you could have order in higher dimensions. The expectation value would not need to go to 0. Okay? So these observations here are exactly in line with what we had seen before for this Mermin-Wigner theorem. Okay, it's another instance of this theorem that we encounter again, and about the order. Okay? Oh yeah, very good. So I did go over time again. Next time I want, yeah, maybe.